Okay, properties of source codes. A code C of x is non-singular if for all x not equal to x prime, C of x is not equal to C of x prime. In other words, each source letter has a unique code word. So clearly, all non-trivial source codes, all practical source codes must be non-singular. If a code word is non-singular, excuse me, if a code is non-singular, then there's no way to distinguish between x and x prime. Excuse me, if a code is singular, then there's some pair x and x prime such that the code words are the same, so therefore we can't distinguish between. So all practical codes are non-singular. So that's not enough though.
So, excuse me, are you saying that has to be a one-to-one function?
Yes, it must be one-to-one. It must be invertible.
Yes. Inverse function.
One-to-one
and onto.
And onto. That's right. So it must be invertible, basically.
Can I ask something else?
Yes.
When you mention L of x, that's in the formula. That's the length of the code words used. So that's the bit size of the.
That's the number of bits. Or if, for example, if my allowed channel alphabet is something else, let's say ternary, and for some x, C of x is 2102 or something, then this is 4. Even though these aren't bits, the length is still 4. So it's just the number of these symbols that make up a code word. Okay, all practical codes are not singular, but that's not enough. So what we need is for when we concatenate two code words together, we still have to be able to distinguish that concatenation from all other possible concatenations. What do I mean? Well, firstly, let's talk about the extension of a code of a source code. So the extension of a code C star, excuse me, the extension C star of a code C of x is the mapping from, okay, so remember my notation from before. We had U star is the set of all finite sequences of U, and U are the allowed channel variables. We're going to have a mapping from X star to U star. Whoops. What does this mean? X star is the set of all sequences of the source alphabet. And U star is the set of all sequences of the encoding alphabet. now we have a mapping not just from letters, but from sequences of letters. And this extension is in particular given by it's the mapping from here to here, continued, given by, if I have a sequence, x1, x2, x3, x4, and so on, this is clearly in x star, up to xn. So this is some finite sequence of x, so clearly that's in x star. Then the extension of that code word C star of x1, x2, x3, x4, and so on up to xn is just the concatenated code words of each of these outcomes. So cx1, cx2, cx3, and so on, cxn. So again, think back to the grading example. If each of these is a grade, then clearly we have a sequence of grades. These could be A plus, A, C, D, so on and so on and so on. What this is telling us is that the extended code, the extension of the code C, is basically the concatenation of all the code words assigned to each of those letters. And this is how we do it in practice. So in fact, we would have a vector of outcomes of x, like so. And what we want to do is we want to, if let's say u is binary, we want to extend this into some binary string. So for instance, x1 will map into a binary string, x2 will map into a binary string, and we'll basically create a binary vector by concatenating all of those code words. So here's an example, just a quick example. Let's say my sample space is A, B, C, and my channel alphabet is 0, 1. And my code words for A, B, and C, let's say code word for A is 0, code word for B is 0, 1, code word for C is 1, 1. Correction, let's make that 1, 0. Then if I want to encode the extended code for A, B, A, C, what would this be? This would be CA, CB, CA, CC, CA is 0, CB is 1, 0, CA is 0, CC is 1, 1. So basically we've just mapped something in x star, some finite sequence of x, into some finite sequence of u. So that's just an extended code. Why are we talking about this? Because we need every unique sequence of these to map into a unique sequence here. We call that unique decodability. So a code, C, is uniquely decodable if its extension is non-singular.